So you saw the Altera computer is coded flipping switches. For that reason, we're going to discuss the binary numeric system, and that will help us understand other concepts such as how memory is measured and how characters are represented. Later on, I will explain to you how pictures appear in computers. The binary numeric system is very special because it uses only two digits, only the 0 and the 1, to represent any numeric value. It was adopted to have these two digits represent power off and power on. 0 is off, 1 is on. So the value 255 in binary is represented as a sequence of 8 switches turned on, or 8 ones. That is 255 in binary. The name binary comes from how many digits we're using to represent values, meaning that bi means 2, so we have 2 digits in this numeric system. The numeric system that we normally use is called the decimal numeric system, and it's called decimal because it has 10 digits to represent any value. So namely, we have the digits 0 through 9, and if you count them, that is 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That represents 10 digits that we have available to represent any numeric value. The numeric systems receive the name that comes from how many digits the numeric system has. If we wanted to have 555 in decimal, that is the value 555. So how does this work? At one point in our education, we learned that our numbers are organized in columns, and each column receives a numeric value. So the 500 is the result of 5 times 100. The 50 is the result of 5 times 10, and the 5 is the result of 5 multiplied by 1. So it's organized in columns, and each column has an implicit column header. The third to the left is 100, the second to the left is 10, and the first one is 1. Where do those values come? They come from the number of digits that we have raised to an exponent. So we also call numeric systems base 10, base 2, etc. So the first column to the right, the rightmost position, is 10 to the 0, the second one is 10 to the 1, and the third one is 10 squared. So the base is represented by the number of digits in the system, and the exponent starts at 0 at the rightmost position, raising it by 1 to the left. Please remember that any number raised to the 0 equals 1. We have other numeric systems, such as the hexadecimal, that has 16 digits. So we would have 16 to the 0, that will be 1, so the column header will be 1. The next one will be 16 to the 1, etc. So please remember, this is very important. Any number to the 0 is 1. So the first column header on the rightmost position is going to be 1 always. So if we're dealing with a binary numeric system, we're going to practice this with 8 columns. And we're going to set up, I'm going to set up for you now the column headers here. So binary, instead of 10 digits, has 2 digits. So it's going to be a base 2 numeric system. So we write down 2 for the base of each one of the 8 columns. And we're going to write the exponent starting with 0. 2 to the 0, 2 to the 1, to the 2, to the third power, and so on, until you reach the 8th to the left column that is going to have the exponent 7, because we started with 0. So when we work those out, the first column is going to be 1, the next one 2, the next one is going to be the previous column multiplied by 2. And when you see these are numbers that are very commonly seen in computer products. So we have a 64-bit console, or we have 128 megabytes in a drive, etc. So when those guys were flipping switches, 1 represents the power on, the switch on. So if we turn on the 32 and we turn on the 8, we multiply the digit by the column header, and that gives us 32 and 8. We add those together, and that is the numeric value 40. So turning on the 32 and turning on the 8 in the Altair or in binary, it represents the number 40 or the value 40. We always fill in the zeros because that represents the switch off, and we spell out a 1 that represents the switch on. So what if I wanted to code the number 10, the value 10, decimal 10? Decimal 10 is not going to look 1 and 0 in binary. It's going to be the 8 plus the 2 that gives us 10. So 0, 0, 0, 0, 1, 0, 1, 0 gives us 10. If I wanted to code 11, then all I have to do is turn on the 1 at the end. So 11 is coded by getting the 8, the 2, and the 1. And don't forget to always write the zeros because that represents the off. Let's code 12. So 12 is a little different because we have two digits that added together will give us 12, which is the 8 and the 4. So we turn 8 and 4 on, everything around off, and that's how you code number 12. Now I'm going to ask you to practice a special value. Value 15. Pause the video and code it and see how that works. Did you code 15 on your own? You should see that you would turn on the last 4 digits of the binary numeric system. So you would have 4 zeros followed by 4 ones. Look at the pattern of this number. It's very unique. 4 leading zeros and then everything on the right of it. This happens on very special circumstances. Look at number 15 is the one we wanted to code. We have a column 16. So that makes the value we want to code pretty special. It's similar to 99 before 100. If we wanted to code 16, we would turn on the 16 and then everything to the right will be 0. But because we're 1 short of 16, we turn everything to the right on. 31 is similar to 16 in that regard. So we have a column 32. We would have 3 leading zeros up to 32, and everything to the right will be a 1, and that will magically add to 31. It's very interesting how numeric systems work. 127, same story, is 1 short of 128, so 0 and all ones. If you work it out, you're going to see that adds to 127. 64, 32, 16, 8, 4, 2, and 1 added together will give you 127. So then I have one more question for you. What value would it be if everything is on? So we learned that 7 ones equals 127, and turning on 128 gives us 128. So it will be the addition of 127 plus 128. How much is that? 255. So what that means is that 255 is the largest value we can code in 8 columns of the binary numeric system. This is a very special concept to remember because the binary numeric system relates to the concept of memory. Each 0 and each 1 that we use to code numbers is what we call a bit. The word bit means binary digit. Every value that we coded was coded using 8 bits, and 8 bits represents the unit we use to measure memory, which is the byte. We say how much memory a computer has, how big a file is, things like that we measure in bytes. So practice these numbers to review, and let's work those out together afterwards. 75. So what do? We grab the first value that fits into 75, which would be 64. If we subtract 64 from 75, which is what we want to code, we're going to get that we need to code 11 more. And 11 is going to be the 8 is the first one that it's going to fit in. And we need 3 more afterwards. So that's going to be 0 for the 4 and 2 and 1 to get 11. So we normally find what's the first column header that fits into the number we want to code. We subtract from it to find out how much more we need to code. And we turn those on, and everything around will be turned off. Incidentally, I cross out the zeros because in computer science we cross out the zeros to differentiate them from the letter O. Okay, 63. We have a column 64, so we turn everything on up to 64, and then everything to the right turn on will be 63. 200 is a little bit more complicated, so we know that 128 fits in. We turn it on and we find out how much more we need to code, and that's going to be 72. So since 64 fits into 72, we turn it on and we find out how much more we need to code after that, and it's going to be 8 because 8 plus 4 is 12, so it adds up. So we turn off the 32 because it's too large. We turn off the 16 because it's too large to code 8. We find the 8 column, we turn that one on, and we're done. So everything afterwards will be zeros. So what about 260? We figure out that 255 is the largest we can code in 1 byte. So we don't have enough space to code 260. We would need more than 1 byte of memory to code the value 260. So if I give you 1 byte, you don't code it, you just say it's too large. We coded 3 values that fit into our memory, so we coded 3 bytes of memory. Each number that we coded used 8 bits, but we measure memory in bytes, so each value used 1 byte of memory. So the last number that I gave you didn't fit in, and that has a name in computer science. It's called data overflow when you have a container that is not big enough for the data you want to code inside. Memory space is limited, and programmers allocate memory in their programs. So when we write programs, we're going to find out how to do that. And different programming languages deal with data overflow differently. So this semester you're going to learn how that works in Python, and in the future you're going to learn how other programming languages deal with that. So in conclusion, the binary numeric system was adopted to be able to code power on and power off. And when we coded the number 15 or the value 15 with 4 leading zeros, it meant that we did off, 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 on, and that was 15 in the Altair. So internally in computers, everything is continuing to work that way, and we don't know that it's working that way. We take it for granted, but internally it works that way, and that's the beauty of programming languages. And also applications that allows us to use different kinds of data. But once that we started to program, we wanted to have text. So how is it that in computers we can have text such as the word aloha? So if we open any text editor, we're able to type in the word aloha. So what they did is that they created tables where each number corresponded to a certain character. One of the first ones that was adopted is this one that is called the ASCII code table. It's spelled ASCII, which we pronounce it ASCII codes. And notice that it gives you what number is for which character. These are the extended characters, the ones that have tildes. ASCII stands for American Standard Coding for Information Interchange. That D at the end is extra. So they decided that they wanted to use 1 byte per character, and that's why the codes will all fit, each one of them will fit in 1 byte of memory. Since the lowest value we can code in 1 byte is 0, and the highest we can code is, which one was the highest number we can code? Do you remember? When we turn everything on, that's the highest value. What was the numeric value of all on? All ones. That was 255. So the ASCII table, including the extended characters, goes from 0 to 255. That represents a total of 256 characters. Each code a different character. So this is the standard ASCII code table, and this is the extended ASCII code table. If we spell out aloha using the ASCII table, each character uses 1 byte, so 5 characters, 5 bytes. There's another table that is standard that is called the Unicode table. It was created by using 2 bytes per character. The first 256 characters are the same as the ASCII codes. So when the Unicode table was adopted, then whatever was created earlier was understood by our computers that are Unicode based. Because ASCII was the first standard, Unicode was born afterwards, and it was done so by using 2 bytes of memory, we can represent all the different character representations that we have in different languages of the world and symbols that we use in computers. So I do not speak all the different languages of the world, so I randomly selected one, and then I scroll down to see the different names of the different languages that are available, and I look for Thai. Being that we are in Hawaii, we are kind of familiar with Thai characters that we see at Thai restaurants. So you can see that that represents the Thai language, what we have on the screen right there. When you click, I like this table specifically online because when you click on a character, it tells you what the code is. Normally, because these codes they get to be so large, it's hard to remember them. So we use the tables. When we want to see these characters in programming, we would say, I want the Unicode 5572, for example, and it will insert the character that is represented by that code. So here we have the Roman numerals, and it shows you 2 codes, and those 2 codes, the first one is in hexadecimal, so it has letters A through F, and the bottom one is the HTML that uses the decimal numeric system. So if you want to spell out a Unicode in decimal, you use the HTML code. Here you have geometric shapes, and if I think the next one that I show is dingbats or something like that. So you see these little symbols that we are familiar with when we work with computers. So these are examples of Unicodes. We can represent these characters in our computers nowadays because we use Unicodes. Is the standard now. And they gave us the Unicodes by using 2 bytes of memory per character. So the word aloha spelled out in our computers nowadays, rather than 1 byte per character is going to use 2 bytes per character, which it will be 10 bytes instead of 5 like before. So those are the character representation, and then the next thing will be to learn about bitmaps.